Welcome to G Fun Facts Online. Today we are not just talking about cold weather, we are talking about the absolute coldest frontier in the universe, a place where physics as we understand it begins to completely unravel. We are diving deep into a breakthrough that happened in June 2024, a moment that physicists have been chasing for nearly 70 years. It is the story of how a team at Columbia University finally tamed the Wild West of the quantum world to create the first stable molecular Bose-Einstein condensate. To understand why this is such a massive deal, we have to start with the concept of temperature. In our daily lives, heat is just movement. The hotter something is, the faster its atoms are jiggling around. But if you go the other direction, if you cool a gas down, you are hitting the brakes on that atomic motion. As you get closer and closer to absolute zero, which is minus 273.15 degrees Celsius, something strange happens. The particles stop behaving like tiny billiard balls bouncing off each other. Instead, they start to behave like waves. This is the quantum realm. According to quantum mechanics, every particle has a wavelength. At room temperature, that wavelength is tiny, almost non-existent. But as the particles slow down, that wavelength expands. If you get them cold enough, those waves start to overlap. If the particles are bosons, they lose their individual identities entirely. They synchronize. They merge into a single superatom vibrating in perfect unison. This state of matter is called a Bose-Einstein Condensate, or BEC. Albert Einstein and Satyendra Nath Bose predicted this nearly a century ago, but it remained just a theory until 1995. That year, physicists finally managed to create BECs using rubidium and sodium atoms. It won them a Nobel Prize and changed physics forever. But here is the catch. Those 1995 condensates were made of atoms. Atoms are simple. They are spherical. They are like smooth marbles. Creating an atomic BEC is difficult, sure, but it is like herding sheep. They are generally cooperative. But physicists did not just want to stop at atoms. They wanted the Holy Grail. They wanted to do this with molecules. Why molecules? Because if atoms are marbles, molecules are complicated machines. They vibrate, they rotate, and most importantly, they have polarity. They offer a richness of physics that atoms simply cannot match. But for 30 years, making a molecular BEC was considered nearly impossible. If atoms are sheep, molecules are like herding cats that are on fire and spinning. Molecules are unruly. When you try to cool them down to the densities required for a condensate, they crash into each other. But unlike simple atoms that just bounce, molecules can chemically react. They can latch onto each other. They release internal energy and blast themselves out of the trap. This was known as the molecular cliff. Every time researchers got close, the molecules would essentially eat each other before they could condense. This problem of collisional loss was a wall that stood for decades. But in June 2024, that wall came down. A team led by Sebastian Will at Columbia University achieved the impossible using sodium-cesium molecules. They created a condensate at 5 nanokelvin. That is 5 billionths of a degree above absolute zero. And even more amazingly, it was stable for 2 full seconds. This sounds short, but in the quantum world, 2 seconds is an eternity. So how did they do it, and why does it matter? Let's break down the physics of this achievement, because the details are fascinating. The reason physicists are so obsessed with molecules, specifically polar molecules like sodium-cesium, is the dipole moment. Most atomic BECs interact through what are called contact interactions. They only feel each other when they literally touch. It is a short-range interaction. It is simple, but it is limited. Polar molecules are different. In a molecule of sodium-cesium, the electrons like to hang out near one atom more than the other. This creates a permanent electric dipole. One end is positive, the other is negative. This means they act like tiny magnets, They can feel each other from far away. This is a long-range interaction. It creates a web of connectivity across the entire gas. Furthermore, this interaction is anisotropic. That is a fancy word meaning direction matters. If you put two magnets head-to-head, they repel. If you put them head-to-tail, they attract. This means the shape of the trap changes the physics. This tunability is a dream for simulating real-world materials. But this strong interaction was also the villain. It was the cause of the cannibalism problem. The attraction pulled molecules together so hard they would undergo sticky collisions, forming temporary complexes that would then explode and eject the molecules from the trap. To make a BEC, you need to perform evaporative cooling. Think of it like blowing on a hot cup of coffee. You let the hottest particles escape, and the remaining ones redistribute their energy and get colder. But this only works if the molecules bounce off each other elastically. If they stick or react, you lose them. For years, the ratio of good bounces to bad losses was just too low for molecules. The breakthrough solution came from a technique called microwave shielding. The Columbia team essentially built a force field around each molecule. They used microwave fields to mix the ground state of the molecule with an excited rotational state. Through the AC Stark effect, this created an energy shift that depended on the distance between molecules. As two molecules approached each other, instead of crashing and reacting, they hit this steep, repulsive potential barrier created by the microwaves. It acts like a virtual bumper car shell. They approach, feel the shield, and bounce off. But the Columbia team went one step further. They used double microwave shielding. They used two separate fields, one circularly polarized and one linearly polarized. This was the magic key. It allowed them to independently tune the shielding repulsion and the long-range dipolar attraction. They suppressed the loss rate by a factor of 10,000. Suddenly, the bad collisions were gone, but the good elastic collisions remained. The path to evaporation was finally opened. The actual experiment is a masterpiece of engineering. It starts with hot clouds of sodium and cesium atoms. They use lasers to cool these atoms to microkelvin temperatures. Then, using a magnetic field technique called Feshbach resonance, they gently coax the atoms to pair up into weakly bound molecules. These are huge, fluffy molecules. To stabilize them, they use a laser technique called STIRAP, which stands for Stimulated Raman Adiabatic Passage. This shrinks the fluffy molecules down into their absolute ground state. Now they have stable sodium-cesium molecules, but they are still too hot, around 300 nanokelvin. This is where they turned on the double microwave shield. With the force fields active, they lowered the trap depth. The hottest molecules evaporated away. The remaining ones bounced off each other's shields, getting colder and colder. As the temperature dropped below 10 nanokelvin, the density distribution changed. A sharp peak emerged in the center of the cloud. At 6 nanokelvin, they observed the smoking gun, a bimodal distribution. They had a dense, coherent core surrounded by a thermal halo. They had created a molecular Bose-Einstein condensate. This new state of matter is not just a trophy. It is a tool that opens the door to physics we have never seen before. One of the most exciting possibilities is the creation of a supersolid. A supersolid is a paradoxical state of matter. It has the rigid, periodic structure of a crystal, but it flows with zero viscosity like a superfluid. In a dipolar BEC, the competition between the repulsion from the shield and the long-range attraction can cause the gas to spontaneously cluster into droplets. These droplets arrange themselves in a lattice, yet they all share the same quantum wave function. They can flow through each other without friction. This is a regime of physics that was previously inaccessible. Another application is studying quantum droplets. These are self-bound blobs of gas that behave like liquid water, holding themselves together even in a vacuum, stabilized purely by quantum fluctuations. But perhaps the most profound application is quantum simulation. Many problems in condensed matter physics, like high-temperature superconductivity, are too complex for even the most powerful supercomputers. A molecular BEC acts as an analog computer. By loading these molecules into a grid of laser light called an optical lattice, researchers can simulate the behavior of electrons in complex solids. Because the molecules interact over long distances, they can simulate spin models where every particle affects neighbors far away. This is crucial for understanding frustrated magnetic systems and exotic states like quantum spin liquids. The stability of this condensate, lasting for 2 seconds, is the game changer. It allows researchers to slowly change conditions, ramping up electric fields or changing geometries without destroying the fragile quantum state. It allows for precision metrology, using the vibrations of molecules to test fundamental constants of nature. It even offers a platform for quantum computing, using rotational states as qubits and dipolar interactions for multi-qubit gates. The creation of the sodium-cesium condensate marks the end of a 70-year quest and the beginning of a new era. We have moved from the age of atomic quantum matter to the age of molecular quantum matter. The rules of this new realm, from fluids that act like crystals to computers built of spinning molecules, are just waiting to be written.